The floor is yours. Oh, so go back.
Okay, so we've got something completely different. Actually, we go back.
Sure.
It's a high-performance arithmetic system. We both like low-level projects and wanted to write something in C. And so we know that the arithmetic can be done really very quickly on local systems, but we want to see how that compared to a distributed system. So we started with our functional requirements, which we'll go through in a little bit more detail. But we wanted different styles of input processing, parallel arithmetic operations happening at the same time, fault-tolerant communication, synchronous result aggregation, performance monitoring and analytics, and also a scalable container orchestration. We knew we were going to lose a lot of the non-functional requirements that you look for in a distributed system, but we thought we might be able to get some scalability out of it. So the distributed input processing, we've got two different ways to input data into the system. One is a client interface where the user can input a computation and it figures it out and displays it back. Very slow. The CSV will take thousands and run them through, and that's what we use for our testing. All of the input is validated regardless of how it's put into the system. The parallel arithmetic operations, this was our computation nodes. We actually did something similar to what you did, Joe. We had the same functions all in the computation nodes. They all have the same exact code. So basically it's split between the computations depending on what operation type it is. And that's how we had the parallel operations going. Our operations were actually quite simple, so we didn't have a whole lot going on at the same time because it happened so quickly. Slide.
So we chose to use MPI because it's more compatible with C. And so we tried to implement a fault-tolerant communication by using a really simple, like, send-receive on MPI with these defined message tags. So by having the message tag, result tag, it would make sure that that send from computation.c would only be received by that display receive. So there wouldn't be like somebody receiving something it's not supposed to. It just prevents that from happening. And also error status tracking. This was stored both within like the MPI status. This one ignores it, but there are other ones where it doesn't. It'll tell you where it came from. So like if something came from the wrong rank, we would be able to know and like say, hey, don't listen to that. And then we also sent termination synchronization. So this was to make sure that all of the computation nodes were shut down and completely done before display fully said, okay, I have everything, let me display. We also made sure everything was synchronized. This kind of comes in with that like termination. So the system synchronized computation results from distributed nodes and maintain consistency through centralized result collection and validation. The display node is that centralized result aggregator. It's where it makes sure that we have all of the expected computations. It's where we validate that they're all done and that the ones that were incorrect are marked incorrect. And then it just makes sure that everything before it is done, before it displays and says to the user, we did it, right? And then we also had timing metrics and throughput statistics and system performance data gathered as we went. So each node like recorded its own time that it took to do its job. And then that was like sent to the final node, and then we got like an average of how long each node took. We got like a summation of all nodes together, the maximum node that took the longest. And these are things we use to calculate the statistics needed for our results, but also statistical analysis of like the data itself, because we were also storing statistics about those as they were coming into the display node, so that they could then be restored with everything else in the CSV that the user eventually gets.
So the architecture design that we ended up with was it was two different architectural designs, a layered system, but also an object-oriented system. This struct here was actually our main object that gets passed back between all of the different files. It has operand 1, operand 2, the operation type, a place for the results, an ID that is sequenced so that you can keep track of order, and a status which was used to reject things that had bad input in them. Slide.
Well, the time was also just used to see how long each computation took to like do the addition, subtraction, or whatnot.
Right, the time is what we use for our performance monitoring. The scalable container orchestration was done through Docker, just like everyone else. As far as like how this can scale, you've got 2 operands and a result. So what we did was addition, multiplication, division, subtraction. But if you have any other formula or algorithm that has 2 operands and 1 output, you can use this same container system. The addition, subtraction, multiplication, division is all enumerated. And so by adding new enumerations, say you had node 5, 6, 7, 8, then it will automatically sort by operation type and send it to the correct node. And the nodes are not reliant on each other, and they don't know that the other nodes exist. So this is the layered architecture that we used. Each of our nodes is an object with only functions and no attributes, and our struct is a object with only attributes and no functions. Starting the user node there, basically that interprets the data and then sends it off to the computation layer. We've got 4 different nodes here, but they all have the exact same code in them. And the user interface actually determines which node gets which computation. Once they finish the computation, it goes to the display node, which processes the information and takes care of the performance monitoring. Once the UI node finishes, it sent all of its computations, follows this line down here to the display node. It sends a termination tag, and it also sends a number of expected results. And this does not complete until the computations match the expected number of computations. That's how we dealt with the race condition there. Once it does, it sends termination tags to each of the nodes, which shuts them down, and then it shuts down itself, so the whole program ends. The UI node, basically it runs, it interprets information, parses through CSV lines, and then sends that data off to the computation nodes, and then we've got a function for the completion signal. This is our computation nodes. They all have the exact same formulas, or the exact same functions in them. Basically, it listens for a request. Once it receives that request, it does a process computation where it decides which type it is, and then sends it to the correct function, which then sends it to the display and logs the computation.
And then the display does a lot. So the display runs, it initializes the output file. It just makes sure if you gave it an output file name or the one we defaulted, it makes sure that it exists before we open it for the first time. And then we listen for results, and then once we receive the results, it starts to store them and organize them and like do the like statistical stuff. So then eventually it can be displayed to the console and printed into the file. So display to console does both. It puts it into the CSV file, but it also prints a couple of key things to the console, so you can see it in both places. And then once it's done, it tells all the computation nodes to shut down so that everything shuts down cleanly. So, and then we clean up any output file stuff, so like if the file had extra stuff underneath it and it's longer than it should be, we just get rid of that. And then for evaluation, we kind of talked about how we got that timing. So we used W time and then MPI reduce. So W time just is kind of like a clock value that you can then do some math and convert it into seconds. And then MPI reduce, this runs at every single node, and it reduces to what you decide. So we did a couple different ones. We did max, we did sum, and so that was how we just got a couple different things. But it just has everybody, and it reduces it to the maximum one. So it'll return, like, inside of total time, it'll just be the maximum time from every single node. So then we would know who took the longest. We did 3 different workloads. Initially, we did eventually add a 4th one because we did small, medium, and large. This kind of ranged from like 48 like inputs, 500 inputs, 1,000 inputs. But if you look at our results, we kind of realized that like we don't see a lot of change between these small inputs, especially in the later stuff. So we added a supersize, and that was like 30,000 inputs. And I think you can kind of see like we did it on the local machine with no MPI at all, and like obviously that has great throughput, and that's just kind of how we were determining what the latency was, so we could see the difference between no like latency at all and like latency now. And then with the distributed on a single node, like that was really a lot of throughput in the beginning, but as we get bigger, it kind of gets smaller, but you see that the distributed gets bigger as we go. So I think that if we were to supersize it even more, there'd probably be a more like benefit to making it distributed, right? And then you can see that latency, like they're kind of on par with each other, but as we increase the amount of like inputs, the latency increase, which, you know, checks out, and then the local kind of just chills.
So this next graph looks really crazy, but don't be confused. The distributed single node did not perform better than the local. There's two different vertical axes here with two different scalings, and so I wanted to be able to show them overlap so you can see the trend lines. With our local system, that actually started off at about 6,500 and went up as the number increased. And then the distributed 4-node system started off and basically increased as the number increased as well. One strange thing that we found was that the single node, whenever we ran it through just one single computation node rather than all four, started off much better than the 4-node, but then parabolically fell into line as the number of computations increased. And I know that that's stacked, but that is not how it looks because of the different scaling. So our results basically determined that the local system operates way better than any distributed system, and the 4-node and the 1-node don't really have that big of a difference at higher numbers. AI usage, I used GitHub Copilot myself for code. It kind of does autocomplete whenever you're coding. And then Claude Sonnet 4 I used for our documentation and just basically cleaning things up and problem solving whenever I needed it. Which you can read all about in the 20-page report that we have that basically has everything that you want to know about the project. And that's it.
Okay. Any questions regarding this 20-page report?